Hello, my friends. So, as we get towards the end of this electrostatics unit, we get to one of the more challenging, one of the more conceptually challenging topics in this entire course. Um, so we're going to again try to use gravitational stuff as an analogy for our electrostatic stuff. But even if we do that, it's still a topic in gravitation that we haven't even talked about. But I hope, using these parallels between the two will at least give it a little more of a foundation. Okay, so let's talk gravity stuff. All right, gravity stuff. Sorry, we say that at location x. All right, here's location x over here. Come on, stop it. Get out of there. Yeah, at location x, right here, there exists, well, a really gravitational field that we call little g. And the strength of little g, hopefully by now we're okay with the fact that if this is, well, who cares what this m is down here? This is some big M. We'll call it g times big M over r squared, where r is the distance from here to there. From the center of that object M, that mass M, to there. Okay? It's measured in newtons per kilogram. Okay? Now, we put a mass at that location or at that same radius, and that mass therefore experiences a gravitational force. Whoops. And that force, Fg, is m times g, or m times, well, m times this. So that's how we get back to our universal gravitational force. Okay? Now, a mass at that location has a certain potential energy. Sorry, I'm just going to move that. And that potential energy we've talked about so far as GPE, and we've called it little m, G, H. Right? Well, that is for us, look, mg is the force, G, m, m over r squared, and h is really r. You get that? So times r allows us to get rid of one factor of r here with that. All right? So we can actually end up with an expression for GPE that is this. GPE is G M M over R. No squared. Okay? So that's something new. Now, let's say we have a bunch of different masses. I'm just going to brush this up a little bit so we're sure that we have big M, little m. The deal is, as long as we're at the same distance away from mass big M, these masses, while they're all different, they'll all experience a different force. They all have different potential energies associated with mass big M. What they have is an equal value of GPE per unit mass, energy per unit mass, right? If we did energy per unit mass and took G M M over R and divided by M, well, we get that. So they have an equal value of, well, like I said, GPE per unit mass, and we call that gravitational potential. Not potential energy. I'm writing this all over again. I don't know why. Okay, so potential is the new concept in this unit. All right, that's really conceptually very abstract, very hard to grasp. I think, but it's energy per unit mass. All right, if we were to put a mass at that location or at a place with a certain potential, well, if we put a mass there, then that mass gets some potential energy because there's potential at that location. Right? I don't even know if there's a, well, I don't know what the variable is for gravitational potential, but I do know that when we go to electricity, there is one for what we call electric potential. All right? So we're trying here to sort of, lay out everything. We got field, we got force, we got potential energy, we have potential. We'll have the same things here in our electricity side of the analog. Oh, now what I didn't do here is, when we talk about gravity, the fundamental entity, the thing that, that dictates everything that's going on, or the thing that we deal with most fundamentally, well, is just mass, right? That's the fundamental entity here. When we deal with electricity, of course, the fundamental entity turns into charge. Right? So everywhere here where we looked at mass stuff, here we'll look at charge stuff. All right? So at a distance away from a charge Q, there's some location X, and at location X, there exists, uh-oh, I gotta scoot for a second. You don't care? I'll just pause the thing. I'll be right back. Again, you don't care? 2 after? I know. I'm back. So, at location X here, I left for 2 hours. I'm back. What do you know? You don't know. You don't know anything. At this place, location X, we say there is an electric field that we call E, and we know the strength of that field is KQ over R squared. Or we also know we can write it as FE per Q. Okay, so therefore, if we take and put a charge at that location, that charge experiences a force that we call K big Q little q over R squared. All right, just like Q times E. All right, if we look back, let me look back to the last page and make sure that yeah, good, right? We said gravitational force is mg, which is gmm over R squared. Here we're saying electrostatic force is QE, which is KQQ over R squared. Okay? Right, get that charge there. Now this charge has potential energy. Poop, you guys are going to be here in 4th block, you're going to be here in 7 minutes. So charges have what we call electric potential energy. Now for whatever reason we call it U. I know it looks like internal energy, right? But it's not. And that U, well, remember, if we do that GPE is mgh, well, the analog here is that instead of mass we use Q, instead of gravitational field we use electric field, and instead of H we use, well, R. Okay, you rarely see it like that, so more often you'll see it as, well, let's see, QE, right, that's the force, which is KQQ over R squared times this R, right, just like we did before for GPE, we have this expression now for electric potential energy, which is KQQ over R. All right, a new one there. I'm locking you out right now, 4th block. Okay, so there's that expression, the new expression for electric potential energy. Get to know it. Now, here's the deal. Just like we said for gravitational stuff, no matter what charge we put there, well, sure, they'll all have different potential energies because those lowercase q's are all different. However, there's the same value of potential energy per unit charge. Okay? And that is called electric potential. The biggest most important new part of this unit, electric potential. Well, I'm sorry, this is also a new and also very important part. Electric potential, potential energy per unit charge, well, that's U divided by Q, so it's just KQ over R. No R squared. All right? Now, the units for electric potential, look here. Right? Well, units of potential energy in the top, joules. Units of charge in the bottom, coulombs. We measure potential in joules per coulomb. Okay? All right. Let's see if we can't use a couple of these bad boys in a simple expression or a simple situation here. We're going to do kind of half of this now and some more of it later. Well, for sure, we can find electric field strength at location X. Well, I know that the field is going to point away from that positive charge. Let's call that E. And E, KQ over R squared, I get 7.2 times 10 to the 7th newtons per coulomb. Okay? Now, potential, one big deal, right? This is vector. This is scalar. Okay, so all we do here, V, KQ over R. I hear you out there, Sarah Torgerson. He's totally in there. 1.8 times 10 to the 6th joules per coulomb. Okay? Potential energy of a proton that we put there, well, that's U, is K cubed Q over R. All right? So, proton we know has the same charge as an elementary charge of an electron. Same charge there. So, let's see, 99 times 5e negative 6 times 1.6 e negative 19 divided by 2.5 e negative 2. I get 2.9, we'll call it, times 10 to the negative 13th joules. Okay? Also, scalar here. Scalar. Okay? Scalar, scalar, vector. Gotta know which ones are which. Okay? I'll be back with part 2 of this video. Peace out.